If atoms are mostly empty space, then why can't you walk through walls, and why don't we fall through the floor? What gives matter its structure, and why do solid objects resist compression? The answer to these questions lies in the Pauli Exclusion Principle and the structure of the wave functions that describe fundamental particles. This principle helps to explain why atoms, and by extension the material world, takes up space. Without it, matter as we know it wouldn't exist. And this is the topic of today's video, so sit back and enjoy the ride. The video is divided into two parts. In the first part, we'll tackle a seemingly simple question. What happens if we place two particles inside a box? This question leads to a profound answer, uncovering the fundamental difference between two categories of particle in the universe, fermions and bosons. In the second part, we'll use Pauli's exclusion principle to understand why solid objects resist compression, and why, even though most of an atom is empty space, you can't push your hand through a wall. We'll begin with a brief recap of one of the simplest possible quantum systems, a particle confined to a one-dimensional box of length L, commonly known as the infinite potential well. Now, if you solve the Schrödinger equation for this system, then you find that the complete wave function describing a particle is given by the following expression, where n is the principal quantum number, and the energy of the particle in the nth energy state is given by the following expression, where h bar is the reduced Planck constant and L is the size of the box. We see from this equation that the energy of the particle is quantized and can only take certain discrete values depending on the quantum number n, and that the spacing between these energy levels grows quadratically with n. The spatial part of the wave function, psi subscript n of x, takes the form of a simple sinusoidal function, with the number of waves fitting inside the box depending on the quantum number n. The wave function encodes information about the likelihood of finding the particle at a particular position in the box. To extract this probability information, we take the modulus squared of the wave function, and this shows us the probability density distribution, indicating regions where we're more likely to find the particle within the box for a given energy state. It then follows that if we wish to find the probability of the particle being located between 2 points x equals a and x equals b within the box, we simply need to integrate the probability density over this particular interval. Okay, so that's the situation when we have one particle in the box. Let's now extend this idea to a more complex scenario involving two particles in the box. For simplicity, we'll assume that there are no forces or interactions between the two particles, and we will also assume for the moment that these particles are distinguishable, meaning we can tell which particle is which, and we can label their individual positions as x1 and x2. Next, if we imagine that particle 1 is in energy state A, then according to the infinite potential well analysis we've already seen, the single particle wave function that we would use to describe this energy state is given by the following green expression, where the spatial part of the wave function is equal to the square root of 2 over L times sine of Na pi x1 over L, and the energy corresponding to this state is given by the following expression. Similarly, if particle 2 is in energy state B, then its wave function and energy take the following form. Okay, so if we now have both particles in the box at the same time, each in their own energy state, what would the combined wave function be? A reasonable first guess is that it would be equal to the product of the individual wave functions. If we then substitute the wave function expressions for each particle, we get the following expression, and this can be simplified by combining the exponential terms. So, does this make sense as a wave function describing two particles? Well, firstly, it's consistent with how energy works for non-interacting particles. When we multiply the individual time-dependent exponential factors, the exponents add together, giving us the correct total energy of the system as the sum of the energies of particle 1 and particle 2. This is exactly what we expect for non-interacting particles. Furthermore, the product wave function also aligns with how probabilities work in quantum mechanics. The modulus squared of the total wave function represents the probability density of finding particle 1 at position x1 and particle 2 at position x2. When we take the modulus squared of our product wave function, we find the following expression, and we see that the exponential terms cancel, leaving the following product. Now, it follows that the probability that particle 1 is between x1 and x1 plus dx1, and particle 2 is between x2 and x2 plus dx2, is given by the following green expression. And this is exactly what we would expect if the two particles act completely independently of each other. The joint probability of two independent events is the product of their individual probabilities. Here, the two particles are independent because they don't interact. And so the likelihood of finding one particle in a particular range has no effect on the likelihood of finding the other particle in its range. Okay, but all of this so far has been based on the assumption that we can distinguish one particle from the other. So what happens if our particles are indistinguishable? Now you might wonder why we would consider such a condition, and the answer is because a truly remarkable aspect of our universe is that every fundamental particle, whether it be an electron, neutrino or quark, is, as far as we can tell, created in an identical manner. This profound uniformity is deeply rooted in quantum field theory, which tells us that fundamental particles represent the smallest possible vibration or excitation of an underlying quantum field. Because all particles of a given type arise from the same quantum field, and each particle represents a quantum of that field, particles of a particular type are inherently identical. It is in this sense that we say two electrons, for example, are identical or indistinguishable. Okay, so what does this mean for us? Well, this means that we cannot, even in principle, distinguish one particle from the other. Their identities are completely interchangeable, and this indistinguishability must be reflected in the joint wave function describing the system. This means that swapping the positions of the two particles should not change the physics, or to be more specific, should not change the probability density, since this is what ultimately determines the physics. So for us, this means it should be true that the modulus squared is the same if we swap the positions of the two identical particles. And this condition reduces to the following condition on the spatial wave functions. So, is this condition satisfied for our two particles in a box? To explore this, let's return to our infinite potential well example. Let's imagine that the two indistinguishable particles are in quantum states labelled A and B. For simplicity, let's consider one particle in the ground state n equals 1 and the other in the first excited state n equals 2. Importantly, saying that one particle is in state A and the other is in state B describes the configuration of the system, not the identities of the individual particles. Since the particles are indistinguishable, swapping them should produce the same physics, and this must be reflected in the symmetry of the probability density. For a particle in the nth quantum state in an infinite potential well, the spatial wave function is given by the following expression, and therefore the spatial wave function corresponding to energy state A and B are given by the following purple expressions. If we then take the product of the spatial wave functions, we get the following blue expression. Whereas if we swap the position labels x1 and x2, we get the following green expression. And we see that these two expressions are not the same. To make this clear, we can plot the two product functions as a contour plot on a set of axes where we've put x1 on the x-axis and x2 on the y-axis. The red shaded areas represent positive values of the product wave function, while the blue shaded areas represent negative values. Notice how the patterns differ between the two plots, reflecting the fact that the two products are not the same. If we then plot the corresponding probability densities for the product wave function in both cases, by calculating the modulus squared of the wave functions, we find that the probability densities also differ. This difference leads to distinct predictions about where the two particles are most likely to be found in the box. And this highlights the limitation of using a simple product wave function to describe indistinguishable particles. Okay, so what is the solution? Well, the solution is to combine the product terms by either adding or subtracting them with x1 and x2 interchanged. For example, we could combine terms like in the following green expression, or we could combine terms like in the following yellow expression. So, why is this better, and what do the subscripts S and A indicate? Well, let's begin by considering the first relation. What happens if we switch x1 and x2? In that case, we see that we get the exact same expression that we started with, and we say that psi subscript S is symmetric under exchange of x1 and x2. That's what the S stands for, symmetric. This tells us that the wave function remains unchanged when we swap the position labels of the two particles. On the other hand, if we take psi subscript A and switch x1 and x2, then we find that we get the negative of what we started with. And therefore we say that psi subscript A is antisymmetric under exchange of x1 and x2. And the subscript A stands for antisymmetric. Now you might wonder, is the minus sign an issue? Well, remember that to determine the probability density from the wave function, we need to calculate the modulus squared. And we see that the probability density remains unchanged under an exchange of x1 and x2. And the same is clearly true for the symmetric combination. Okay, but given that both symmetric and antisymmetric combinations lead to probability densities that remain unchanged under the exchange of x1 and x2, which one should we use for our two particles in the box? And is there a difference? To answer this question, let's revisit our contour plot, this time plotting the probability density associated with the symmetric and antisymmetric combinations directly. This will give us a clearer picture of how these two types of wave functions influence the likelihood of finding the particles in specific locations inside the box. First, let's plot the probability density corresponding to the symmetric combination. Specifically, we'll consider the case where one of the particles is in the ground state and the other is in the first excited state. In this case, the modulus squared of the symmetric combination is given by the following expression. So what does this look like? Well, if we plot the probability density as a contour plot with x1 and x2 as our axes, we find the following plot. Now, the first thing that we note is that the plot is symmetric about the line x1 equals x2. Which means that if we were to switch the labels of our axes, it would make no difference to the probability density. This is precisely what we want, given that our particles are indistinguishable. The next thing we note is that there are two peaks in the plot, and both peaks lie exactly on the line x1 equals x2. This is telling us that when our two particles are described by a symmetric wave function, the probability density is at its highest value when the particles are located at the same position. The takeaway message is that a symmetric wave function describes particles that tend to bunch together in space. Okay, but what about the antisymmetric combination? If we again assume that one particle is in the ground state and the other is in the first excited state, then the modulus squared of the antisymmetric wave function combination is given by the following expression. So what does this look like? If we plot the corresponding contour plot, we find the following pattern. As with the symmetric case, the probability density is symmetric about the line x1 equals x2, meaning that there is no difference if we were to switch x1 and x2, as should be the case for indistinguishable particles. However, we now see something remarkable and fundamentally different from the symmetric case. The probability density is 0 along the line x1 equals x2. This means there is absolutely no chance of finding both particles at the same location. Instead, the probability density peaks when the two particles are separated in space, indicating a preference for the particles to avoid each other. And this is completely different to the symmetric wave function case. And so to summarise, for the symmetric wave function, the probability density is highest when the particles are at the same location. suggesting a tendency for the particles to bunch together. In contrast, for the antisymmetric wave function, the probability density is 0 when the separation is 0, suggesting a tendency for the particles to stay away from each other. And it is worth emphasizing that this has got nothing to do with forces. In our model system of two particles in a box, we assumed that there was no interaction between the two particles, no forces whatsoever. However, we have seen that the requirement of particle indistinguishability means that we must use either a symmetric or antisymmetric wave function, and depending on which we use, the two particles will either tend to bunch together or stay apart. Now, at this stage, it would be reasonable to ask whether this is unique to the particular combination of quantum states that we chose. If you recall, we said that one particle was in the ground state and the other was in the first excited state. But could we have chosen any other combination of quantum states? For example, if we considered a case where one of the particles is in the ground state, n equals 1, and the other is in the second excited state, n equals 3, then we would find the following probability density plots. And again, we see that the probability density peaks for the symmetric case when x1 equals x2, and it's 0 along the line x1 equals x2 for the antisymmetric case. And similarly, if we plotted the case corresponding to one particle in the ground state and one in the third excited state, we see the same pattern again, with peaks occurring along the line x1 equals x2 for the symmetric case and zeros for the antisymmetric case. And finally, if we look at the n equals 2 and n equals 4 case, we find the following plots. And we could continue playing this game with any combination of different quantum states, and we would always find that by combining the product of wave functions in a symmetric fashion, we find that there's a high probability that the particles will be located at the same position, and for an antisymmetric combination, there is 0 chance that the particles are located at the same position. Okay, so far we've only considered cases in which the energy states of the two particles are different, which leads to a natural question. What if the two particles have the same energy state? In other words, what happens in the case where A equals B? And this corresponds to the quantum numbers being the same, which then of course means that the energies of the two particles are the same. Well, in the case of a symmetric wave function, if we set A equal to B, then we find the following yellow expression, and we see that this is clearly non-zero. On the other hand, if we consider the antisymmetric wave function and set A equals to B, then we see that the antisymmetric function becomes exactly 0. And so this is telling us something that's quite interesting. It's not possible to describe two particles that are in the same energy state with an antisymmetric wave function. We can only use a symmetric wave function. Okay, let's take a moment and summarise. We have found that if two indistinguishable particles are in the same energy state, then their spatial wave function must be symmetric. On the other hand, if two indistinguishable particles are in different energy states, then their spatial wave functions can be either symmetric or antisymmetric. If symmetric, then the particles will tend to bunch together, and if antisymmetric, the particles will stay apart. And most importantly, this behaviour has nothing to do with forces, but rather a consequence of the symmetry or antisymmetry of the wave function. Okay, but believe it or not, this is still not the complete picture. To deepen our understanding of the situation, let's now consider the case where both particles are electrons. This introduces an additional layer of complexity because, as you may have heard, particles like electrons possess an intrinsic form of angular momentum known as spin, and we need to take this into account when defining our overall quantum state. Now, spin is a purely quantum mechanical property with no direct classical analogue. While the term spin might suggest that the particle is physically rotating, this is not the case. Instead, spin refers to an intrinsic property of particles that shares some mathematical similarities with angular momentum. For our purposes, it's enough to understand that an electron's spin can be described as being either aligned or anti-aligned with a chosen coordinate direction, typically chosen to be the z-axis. Furthermore, electrons are classified as spin half particles because when we measure their spin along the z-axis, the result is always one of two discrete values, plus 1/2 h bar or minus 1/2 h bar, where h bar is the reduced Planck constant. These two possible outcomes correspond to the electron being in a spin up or spin down state relative to the chosen axis. Okay, so let's now return to our two particles in a box and imagine that they are both electrons. Now, if one of the electrons is in a spin up state, we can represent this as U brackets 1, where U indicates spin up and the 1 refers to the first electron. Similarly, if the other electron is in a spin down state, we can represent this as D brackets 2, where D indicates spin down and 2 refers to the second electron. Then, for instance, a combination such as U1D2 would describe a situation in which the first electron is spin up and the second electron is spin down. Using this approach, we can write the following product combinations. Now, electrons are indistinguishable particles, meaning it shouldn't matter how we label our two particles. Under this constraint, only the first two product states are symmetric, since U1U2 is equal to U2U1 and D1D2 is equal to D2D1. However, it's clear that U1D2 is not the same as U2D1 and D1U2 is not the same as D2U1. To satisfy the indistinguishability requirement, we can combine these two states into either a symmetric or antisymmetric combination. The symmetric combination is written by adding the two states, and the antisymmetric combination is written by subtracting one from the other. If we examine these combinations more closely, we can clearly see that swapping the labels of the two particles in the symmetric combination does not change the spin function. In contrast, swapping the labels in the antisymmetric combination introduces a negative sign. And so we see that, in total, there are 3 possible symmetric spin states, and there is 1 antisymmetric spin state. The first of the symmetric spin combinations corresponds to both particles being spin up. Now, since the spin projection along the z-axis for each particle is half h bar, it follows that the total spin projection for this state is plus 1 times h bar. Similarly, the second symmetric combination corresponds to both particles being spin down, and in this case, the total spin projection along the z-axis is equal to minus 1 times h bar. The third symmetric spin combination represents a state where one particle is spin up and the other is spin down. Here, the spin projection along the z-axis cancels, and therefore the resulting total spin projection is equal to 0. Finally, the antisymmetric spin state, which corresponds to one spin up and one spin down, also has a total spin projection along the z-axis of 0, but it is antisymmetric under particle exchange, as indicated by the subscript A. Now, armed with this new understanding, let's return to our example of 2 identical electrons in a box. To describe the total state of both electrons, we must combine their spatial wave functions and spin states. And we can do that in the following ways. First, we can have a symmetric spatial wave function and a symmetric spin state. Second, we can have an antisymmetric spatial wave function and an antisymmetric spin state. Third, we can have a symmetric spatial wave function and an antisymmetric spin state. And finally, we can have an antisymmetric spatial wave function and a symmetric spin state. We note that the first 2 product combinations are symmetric under exchange of the 2 electrons, meaning that the total product combination remains unchanged when both position and spin labels of the 2 particles are swapped. In contrast, the last 2 combinations are antisymmetric under exchange. So the natural question arises, which of these combinations should we use to describe the two electrons in our box? Now, it turns out that the answer to this question depends on the type of quantum particles that we have in our box. You see, quantum particles fall into two broad categories, bosons and fermions. Bosons are particles with integer spin, meaning that when a boson's spin is projected onto the z-axis, the result is an integer multiple of h bar. Fermions, on the other hand, are particles with half-integer spin, meaning that when a fermion spin is projected onto the z-axis, the result is a half-integer multiple of h bar. And it turns out that when dealing with multiple particles, bosons must be described by a total wave function that is symmetric, whereas fermions must be described by a total wave function that is antisymmetric. This remarkably deep connection between spin and the symmetry properties of wave functions is encapsulated in the spin statistics theorem, a fundamental result in quantum field theory. Now, while a deeper explanation of this theorem is beyond our current scope, it suffices to note that this principle governs the wave function behaviour of all quantum particles. Okay, so how does this help us to understand our two electrons in a box? Well, electrons are fermions with spin half. Therefore, according to the spin statistics theorem, the total wave function of two electrons must be antisymmetric under the exchange of particles. And this requirement determines the allowable combinations of spatial and spin states. And as we've already seen, in the case of a two-electron system, there are only two ways in which we can construct a total wave function that is antisymmetric. The first option is to combine a symmetric spatial wave function with an antisymmetric spin state, and the second option is to combine an antisymmetric spatial wave function with a symmetric spin state. Okay, so then what? Let's start by considering the first of the two product combinations, a symmetric spatial wave function combined with an antisymmetric spin function. For now, we will focus on the scenario where the two electrons are in different energy states, which, if you recall, means that they have different values for the quantum number n and therefore different energies. Now, for this product combination, the spin state is antisymmetric, which means that the two electrons must have opposite spin, as can be seen explicitly from the antisymmetric spin function. Furthermore, the fact that the spatial wave function is symmetric tells us that the probability density is at its maximum when the two particles are at the same location. This means that for the case of different energy states, the product between a symmetric spatial wave function and an antisymmetric spin function describes two electrons with opposite spin that have a very high probability of being located at the same position in space. On the other hand, if both electrons have the same spin direction, then if you recall from earlier, this means that the spin state has to be symmetric, and therefore the spatial wave function must be antisymmetric, such that the total wave function is antisymmetric in line with the spin statistics theorem. Now, if you recall, the structure of the antisymmetric spatial wave function means that when we construct the corresponding probability density, we find that there is zero probability that the electrons will be found at the same spatial location. And so we see that in the case of different energy states, two electrons with the same spin will not be found in the same spatial location. Okay, so to recap, if both electrons are in different energy states, then they can be described by two possible product combinations, a symmetric spatial wave function and an antisymmetric spin state, or an antisymmetric spatial wave function and a symmetric spin state. In the first case, we found that a symmetric spatial wave function implied both electrons have a high likelihood of being at the same location and they must have opposite spin. On the other hand, we found that if both electrons have the same spin, then they must have a symmetric spin state, which means that they must also have an antisymmetric spatial wave function, meaning that they have a high probability of being separated in space at different locations. And this situation is described by the second product combination. Now, the sharp-eyed amongst you may have noticed that there is a possible scenario that I have not yet mentioned, the case of opposite spin electrons described by a symmetric spin state. In this case, the spatial wave function must be antisymmetric to ensure that the total wave function remains antisymmetric. This implies that the opposite spin electrons must be spatially separated and occupy different energy states. Okay, but what if our two electrons have the same energy state? What happens then? Well, if you recall, if one electron is in energy state A and the other is in state B, then as we've already seen, the spatial wave function can either be symmetric or antisymmetric. And if we now set A equals to B, such that both electrons are in the same energy state, then we see that the antisymmetric spatial wave function vanishes. Whereas, if we look at the symmetric combination and set A equal to B, we see that the result is not zero, and therefore we see that if both electrons are in the same energy state, then they must be described by a symmetric spatial wave function. And a symmetric spatial wave function requires that the spin state be antisymmetric, such that the total wave function is antisymmetric overall. And therefore, we see that if the two electrons are in the same energy state, then it's impossible for the electrons to have the same spin direction, since this would require the spin state to be symmetric, whereas we've just seen that it must be antisymmetric. And so we are led to a remarkable result. It is fundamentally impossible for two electrons to occupy the exact same quantum state, having the same energy and spin, because in such a case, the total wave function will necessarily be zero. This implies that there is zero probability of this occurring, and this profound result is known as the Pauli Exclusion Principle, a cornerstone of quantum mechanics. Now, remarkably, Wolfgang Pauli deduced this principle in 1924, long before the development of the Schrödinger equation and the formal understanding of wave functions. Rather, he inferred it from patterns in atomic energy levels revealed through spectroscopy. So, what does this all mean for our electrons in a box? Well, to see the profound consequences of the Pauli exclusion principle, let's see what happens if we try to add multiple electrons to our box, one at a time. Recall that physical systems naturally minimize their energy. It follows that if we add one electron to our box, it will occupy the n equals 1 ground state to achieve the lowest energy. Since there is only one electron, it doesn't matter whether it's spin up or spin down, as either spin state can occupy the ground state. Next, imagine adding a second electron. If the electron has spin up, it cannot occupy the n equals 1 ground state, because this would violate the Pauli exclusion principle, which prohibits the two electrons from having the same energy and spin. Instead, the second electron must occupy the next available energy level, which is the n equals 2 level, resulting in a total energy of E1 plus E2. Okay, but what if the second electron had spin down? Well, in that case, it could share the n equals 1 ground state with the spin up electron, because although they have the same energy, their spin states are different, and this is allowed by the Pauli exclusion principle. In this case, the total energy would be equal to 2 times E1, which is lower than the energy configuration for two spin up electrons. Okay, so let's imagine the n equals 1 ground state is now fully occupied, and consider adding a third electron. Regardless of its spin, the third electron cannot occupy the n equals 1 ground state because both spin states at this energy level are already filled. The only option is for the third electron to occupy the next available energy level, which is the n equals 2 state, and similarly, a fourth electron can also occupy the n equals 2 state, provided its spin is in the opposite direction to that of the third electron. This process continues as more electrons are added. Successive electrons must occupy higher energy levels once the lower energy levels are filled with electrons of opposite spin. The Pauli Exclusion Principle thus forces electrons to stack into progressively higher energy states. This simple but profound rule has significant consequences for the structure of matter, as we will now see. Okay, so let's now extend our analysis to a three-dimensional cubic box of side length L, from which it's impossible for an electron to escape. Rather than considering a one-dimensional infinite potential well, we will explore what happens as we add more and more electrons to this cubic box, under the constraints of the Pauli Exclusion Principle. Now, if you recall, in the one-dimensional case, the energy states were given by the following expression, where n is the quantum number that labels each energy state. The good news is that in 3 dimensions, the energy expression easily generalizes, where the 3 quantum numbers nx, ny and nz reflect the fact that we're operating in 3 dimensions of space, and where we've simply replaced n squared from the one-dimensional case with nx squared plus ny squared plus nz squared in the energy equation. Now, to visualize what's going on, we introduce a set of nx, ny and nz axes to form a 3-dimensional lattice in n space. Each point on this lattice represents a unique combination of nx, ny and nz, and therefore corresponds to a particular energy state. The points in the n space are uniformly distributed across the lattice, meaning that the quantum numbers nx, ny and nz increase in regular integer steps. Now, each unit cell in the lattice represents a single block in n space, and the volume of each block is equal to 1, since 1 times 1 times 1 equals 1. Now, while it might seem like a unit cell has 8 vertices, it's important to note that each vertex is shared amongst 8 adjacent cells in the 3D lattice. As a result, each unit cell contributes exactly 1 unique lattice point to the system. This means that there is 1 energy state associated with each unit block in n space. Now, the Pauli Exclusion Principle tells us that no 2 electrons can occupy the same quantum state. This means that each point in n space corresponding to an energy state can accommodate at most 2 electrons, one with spin up and one with spin down. Next, imagine adding electrons to the system one at a time, starting with the lowest energy states, those with smallest values of nx squared plus ny squared plus nz squared, and then placing 2 electrons in each energy state, one with spin up and one with spin down. As more electrons are added, progressively higher energy states are filled. Now, when the number of electrons, n subscript e, becomes very large, the occupied points in n space form a roughly spherical distribution. This is because the energy of each state depends on nx squared plus ny squared plus nz squared, and states with the same energy lie approximately on the surface of a sphere in n space. The radius of this sphere defines the boundary of the filled states and is known as the Fermi radius, n subscript f. It then follows that the energy of the states at this boundary is given by the following expression, where nf squared equals nx squared plus ny squared plus nz squared. And this represents the maximum quantum number radius of the filled states. And the corresponding energy, E subscript f, is referred to as the Fermi energy, named after the quantum pioneer Enrico Fermi. Now, since the unit volume in n space is equal to 1, and each unit volume corresponds to exactly 1 energy state, the number of energy states within a sphere of radius nf is simply equal to the volume of the sphere. However, because nx, ny and nz are restricted to positive integers, the filled states occupy only the positive octant of the sphere. The volume of the positive octant of the sphere is then given by 1/8 times 4/3 pi nf cubed. Then, since each energy state can accommodate 2 electrons, one spin up and one spin down, the total number of electrons is equal to twice the volume. and this simplifies to pi nf cubed divided by 3. If we then rearrange this expression, we find that nf equals the cube root of 3ne over pi. It follows that the energy corresponding to the outermost highest energy occupied states is the energy state at radius nf, and is given by the following expression. If we then substitute our expression for the Fermi radius, we get the following green expression, which we can then write in the following form, where we've used the fact that the volume of the box is equal to L cubed. Finally, if we define the electron number density as the number of electrons divided by the volume, then we find the following expression for the Fermi energy, and this represents the energy of the highest energy electrons among all occupied energy states. Okay, but how would we find the total energy of all occupied states? Firstly, consider the total energy of all states lying within a thin spherical shell of width dn at a radius n equals the square root of nx squared plus ny squared plus nz squared. The total energy of states within this shell will then be equal to the volume of the thin shell multiplied by the energy of a state with radius n multiplied by 2 to take account of the fact that 2 electrons can occupy each energy state. The volume of this thin shell will be equal to 1/8 the surface area of the sphere, 4 pi n squared, multiplied by the thickness dn, and we already know the energy of a state with radius n is given by the following expression. We can then combine these results to write the energy in the following form. Simplifying this expression, we find the following result. It then follows that if we wish to find the total energy of all states from n equals 0 to n equals nf, we simply need to integrate this expression between those limits. And if we sub in our energy expression, we find that the total energy is equal to pi cubed h bar squared nf to the power of 5 divided by 10mL squared. Next, we can sub in our expression for the Fermi radius, and we find the following expression, which we can write in terms of the volume V. Okay, so what is this telling us? Well, firstly, we see from this relation that the total energy is proportional to the volume raised to the power of negative 2/3. If we plot energy as a function of volume, keeping the number of electrons inside the box fixed, we see that as the volume of our box gets smaller, the total energy rapidly increases. In other words, if we squeeze our electrons into a smaller volume, corresponding to V decreasing, the energy will increase. This is telling us that it costs energy to compress the box of electrons. This is ultimately a consequence of the Heisenberg uncertainty principle. As the electrons are confined to a smaller space, their positional uncertainty decreases, forcing their momentum uncertainty to increase, which raises their kinetic energy. We also note that the energy is proportional to the number of electrons raised to the power of 5/3. If we plot the energy as a function of the number of electrons, keeping the volume of the box fixed, we see that as the number of electrons increases, the total energy rises rapidly. This is because additional electrons are forced to occupy higher energy states in order to obey the Pauli Exclusion Principle, since the lower energy states are already filled. Since the energy of a given state scales as n squared, these higher energy states contribute significantly more energy than the lower ones, leading to a rapid rise in energy as the density of electrons increases. Now, we can actually use our energy equation to calculate the pressure caused by these quantum mechanical effects. From the laws of thermodynamics, we know that the pressure is related to the rate of change of energy with respect to volume, according to the relationship P equals minus dE by dV. If we then apply this to our energy equation, we find the following ghastly expression, and we can then rewrite this in terms of the electron number density, and we find the following yellow expression. And so we see that the pressure depends on the 5/3 power of the number density. This means that as the electron density increases, the quantum mechanical pressure grows rapidly, providing a mechanism to resist further compression. To see this relation more clearly, we can plot the pressure as a function of the electron number density. This is telling us that as electrons are compressed into smaller volumes, their number density increases and the pressure rises rapidly, resisting further compression. This behaviour is a purely quantum mechanical effect. Firstly, the Heisenberg uncertainty principle ensures that confining electrons to smaller volumes increases their momentum uncertainty, leading to higher kinetic energy, even if the electrons were all in the lowest energy state. Secondly, the Pauli Exclusion Principle adds a uniquely fermionic contribution to the pressure. It prevents electrons from occupying the same quantum state, forcing them into higher energy levels as the density increases. This stacking of electrons into successively higher energy states greatly amplifies the total energy and thus pressure. At high electron densities, this exclusion-based Pauli pressure dominates over the contribution from the uncertainty principle alone. Importantly, this resistance to compression is independent of electrostatic repulsion or thermal pressure, and arises purely from quantum mechanics, and it provides profound insight into why solid matter does not collapse under applied forces. To make this even more concrete, we can apply these ideas to understand the behaviour of conduction electrons inside metals. The high number density of these electrons creates a system where modelling them as particles confined in a box provides a reasonable and insightful approximation of their behaviour. The resistance to compression of a material can be quantified using a property known as the bulk modulus, which is defined as kappa equals minus v times dp by dv. The bulk modulus measures the resistance of a substance to bulk compression. It's defined as the ratio of an infinitesimal pressure increase to the resulting relative decrease in volume. For metals, the high quantum pressure arising from the Pauli exclusion principle plays a significant role in determining their resistance to compression. If we take this bulk modulus equation and then substitute in the expression for the quantum pressure that we derived earlier, we find the following expression for the bulk modulus. As an example, consider magnesium, which has a free electron number density of approximately 8.6 times 10 to the 28. Using this value, the bulk modulus is estimated to be 6.4 times 10 to the power 10 newtons per meter squared. This is remarkably close to the experimentally measured value of 4.5 times 10 to the power 10. This agreement demonstrates how the quantum mechanical Pauli exclusion principle accounts for the resistance of metals to compression, ultimately explaining their structural integrity and solidity. And so, this brings us to the end of our quantum mechanical journey. We have seen how the Pauli exclusion principle explains why fermions cannot all collapse into the lowest energy state. And this is ultimately the reason why atoms are organised into distinct shells, shaping the periodic table, enabling the rich complexity of chemistry, and ultimately making life itself possible. But perhaps most remarkably, it answers the deceptively simple question of why you can't push your hand through a wall. Because the Pauli exclusion principle ensures that the electrons in your hand and those in the wall resist being forced into the same quantum state, creating an impenetrable barrier and giving matter its reassuring solidity. It feels only appropriate that we end with a quote from Pauli himself. One should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same, than about the ancient problem of how many angels are able to sit on the point of a needle. Thank you for watching, and until next time.